So in this lecture, we will focus on the study of symmetrical components in order to analyze three-phase unbalanced circuits. So unbalance could be in respect of the fundamental and the harmonics. First, we will focus on the unbalance with respect to fundamental only. The concept of symmetrical component was proposed in 1918 by C.L. Fortescue, who has given the theorem for n-phase system. C.L. Fortescue in 1918 presented a paper about n-phase unbalanced system. So according to the proposition of C.L. Fortescue, n-phase unbalanced system can be resolved in n-1 balanced phasors and 1 co-phasor. So total n phasors, n set of phasors, n-1 plus 1. But n-1 are balanced phasors, while the remaining one forms the co-phasors. The co-phasors is not called as balanced phasor because they are co-phasors, they are in the same direction, they have same phase angle. So this concept of n unbalanced phasors or n phase unbalanced system was applied to three-phase unbalanced system. So obviously n-1 becomes 2 because n is equal to 3. Three-phase unbalanced system can be resolved in 2 balanced phasors and 1 co-phasor. These 2 balanced phasors basically termed as positive sequence and negative sequence, and the remaining co-phasor is defined as zero sequence component. Thus we form positive, negative and zero sequence components. We normally denote three-phase system either by ABC phases or by R by B. In some notations it is RTU. As per our electricity board authority, we use either ABC or R by B. So R by B stands for red, yellow and blue. If you see the cable then and open the cable, you will see the three-phase system cable has 5 wires: red, yellow, blue, black, BL, and then there is also green wire. So red is for phase 1, that is A, the yellow is second phase, the blue is third phase, R by B, and black is for neutral, okay, and green is for ground. The neutral is run parallelly to the phases and finally it is grounded somewhere along the line or at the towers or at building at different places. So these are the 5 colors which are used for denoting the phases, neutral and earth. In ABC notation we use A for first phase, B for second phase, C for third phase, and then we use the black and green for neutral and ground. Okay, I hope you all will be knowing this, just to remind you that what is the notation of the phases in the three-phase system. So these R by B or ABC sequence basically is called positive sequence because B follows A and C follows B, and then again A follows C. So ABC or CAB. If I write this also as BAC, it is same sequence, BCA or CAB or ABC. They are same sequence and they form the positive sequence. But there is a negative sequence. So negative sequence, the sequence is changed. It becomes ACB. Okay. or it becomes CBA. Anything, any version of this is called basically negative sequence. And for zero sequence, we denote either AAA or BBB or CCC or 000 because they are co-phasors, the direction is same. So we have positive sequence, then negative sequence and zero sequence. If you denote in terms of phasor diagram, then this will form a positive sequence. If I say that this is the axis A, this is the axis B, this is axis C. They are 120 degree apart, and B follows A and C follows B. A follows C and so on. So I can say the B lags AY 120 degree and C lags BY 120 degree and A lags CY 120 degree. And these positive sequence are denoted as BA plus, BB plus, BC plus, plus for positive. Okay, so this term is basically for positive. Minus for negative, so this is for negative sequence. A for A phase, B for B phase, C for C phase, and 0 is used for zero sequence. If these phasors have their corresponding positive, negative and zero sequence for each phase, then if I sum them up, we will get the overall phasor. For example, the BA therefore must be sum of BA plus and BA minus plus BA 0. Similarly, the B phase phasor or voltage phasor will be the sum of BB plus, BB minus and BB 0. The bar is used to denote the phasor. And similarly, we have BC. So BC is nothing but BC plus, BC minus, BC 0. Forming the positive sequence, these components form positive sequence. These form negative sequence. Okay, and this forms zero sequence. For each phase has positive, negative and zero sequence. And together, the positive, negative and zero of any phase forms the overall phasor of that particular phase voltage. Now I have shown here the axis notation. This is a normal notation for axis ABC in three-phase circuits. A is a complex operator which is also written as e to the power j 2 pi by 3. What is this? One angle of 120 degree. And that is nothing but minus half plus j root 3 by 2. Similarly, a square is to the power j 4 pi by 3, or you can say to the power minus j 2 pi by 3, which is one angle of minus 120 degree, and that means it is minus half minus j root 3 by 2. And also there is one property of this complex operator, that is 1 plus a square equal to 0. Now let us try to correlate these positive and negative sequence component in terms of the BA plus, BA minus, BA 0. Because since we know their nature, that is positive and negative sequence, then we can write only in terms of A plus, A minus, A 0, because B plus can be expressed in terms of A plus. Similarly, C plus can be expressed in terms of the A plus. So to understand this, we will try to correlate these parameters. For example, BA plus is same as BA plus, so this is my reference point. BB plus should be lagging BA plus by 120 degree. Okay, and 120 degree minus, lagging means minus, so 1 minus 120 degree is A square. As you have seen it here, this is A square. So A square is 1 angle of minus 120 degree. So I will write BB plus as A square BA plus. Okay, similarly we can express BC plus. Now BC plus will be leading BA plus by 120 degree because it is positive sequence. You can see from here, this is BC plus. This will be leading BA by 120 degree. You can see here, this is the leading. And hence, this is BA plus angle of 120 degree. 1 angle of 120 degree is nothing but A. So we substitute as A. So BC plus bar or BC plus phasor becomes BA plus angle of 120 degree, that is A BA plus. So this is the relationship between the BA plus, BB plus and BC plus. Similarly, we can form the relationship between the negative sequence components. So let BA minus be same as BA minus, a reference point. Then BB minus will be, now sequence is opposite, it's a negative sequence. In negative sequence, the B phase is leading A phase by 120 degree. Okay. For example, if this is the positive sequence here, this is BA plus, then this will be BB plus, this will be BC plus. But for negative sequence, it will be like this, that we have BA minus, then this will be BC minus, because this is negative sequence. This time C will be lagging A by 120 degree. Okay, and this will be here. This will be B minus. So sequence has changed. This is negative sequence. This is positive sequence. Okay, and for zero sequence, they are co-phasors. So this is BA0, this is BB0, this is BC0. They are same. So BA0 you can say equal to BB0 equal to BC0. So therefore BB minus will be BA minus angle of 120 degree, and it becomes nothing but A BA minus, because A is 120 degree, and BC minus will be BA minus angle of minus 120 degree, that becomes A square BA minus. So now we know the relationship between the negative sequence quantities and the positive sequence quantities, and the co-phasors is BA0 equal to BB0 equal to BC0, as you can see from here. So this is the zero sequence phasor, which is collinear. They are co-phasors and they have same value as shown here, BA0, BB0, BC0. Now we can write these expression in form of the matrix. So you can write here that this is same as BA plus, BA minus is nothing but BA minus, this is same, this is BA minus here, plus BA0, and BB phasor will be BB plus, which is A square, it's A square BA plus. BB minus is A, BA minus. and plus BB 0, which is same as BA 0. And the third one is BC plus is nothing but A BA plus. BC minus is A square BA minus, and this is again BA 0. So these equations are written in form of the matrix. BA is 1 1 1, so this is 1 1 1, BA 0, BA plus, BA minus, and then BB phasor is A square BA plus. So this is A square BA plus and A into BA minus and 1 into BA 0. This is the second row. The third one is here, which indicates the value of BC minus. BC minus is BA 0 plus A into BA plus, this one, and then plus A square BA minus here. Okay, so this is called as symmetrical transformation, where we express unbalanced three-phase voltages BA, BB and BC in terms of the BA 0, BA plus and BA minus. That is positive, negative and zero sequence component. Similarly, we can express for current as well. So current we can also express, this is I here, IA 0, IA minus, IA plus here, then IA minus here. Close this bracket. So this is for voltage, this is for current, but this is a positive sequence component in terms of the voltage. How this is achieved? By taking inverse of this matrix. So let us denote this matrix as A matrix. Okay, let us denote this matrix as a matrix, that is ABC, ABC, which transform sequence quantities to ABC quantities. Right now we are transforming B0 plus minus to BABC. Therefore, B0 plus minus will be nothing but AABC inverse, it is here, into BABC becomes V0 plus minus. So B0 plus minus becomes A0 plus minus into BABC. So what is relationship between this one and this one? Obviously A0 plus minus is nothing but inverse of AABC. So when this matrix is A0 plus minus, then it transforms ABC voltage to 0 plus minus. When the matrix is ABC, then it transforms zero sequence, positive sequence, negative sequence component to ABC. Now this is also shown here in terms of the phasor notations. For example, there is a three-phase unbalanced system. Okay, and that three-phase unbalanced system is resolved in three phasors, in which two are the balanced phasors, positive and negative sequence, and the remaining is a co-phasor, zero sequence component. So as you can see from here that this is the BA plus, this is the BB plus, this is the BC plus. This sequence is ABC in fact, so we can write it ABC sequence or positive sequence. And this forms, the second figure is showing the negative sequence component, that is, this is suppose BA minus, then this is BC minus, this is BB minus. The sequence is here ACB, or you can say ACB. This forms the negative sequence. And finally, this is the co-phasor, or you can say zero sequence. In co-phasors, the co-phasors are having the same magnitude and same phase angle. Now, if you find out BA from this, so obviously this is BA. So BA is sum of BA plus, BA minus plus BA 0. You can see this is BA plus. This is BA plus. What is BB plus? This is BB plus here. What is BC plus? This is BC plus. You see, these are balanced phasors, positive sequence balanced phasor. Similarly, you have a BA minus. This is BA minus. This is BB minus. See, nature, balanced negative sequence. This is BC minus. Should be this direction. Okay, this also balanced phasor but negative sequence. And finally, there is a zero sequence. This is zero sequence co-phasor. This is zero sequence co-phasor. This is zero sequence co-phasor here. They are same direction. Okay, so you can resolve any three-phase unbalanced system into positive, negative, and zero sequence component. And from the phasors, we can connect its positive sequence component among the phases, negative sequence among phases, and zero sequence. And based on that, we formulate a matrix relationship between these points, between these parameters. So therefore, we can write first BABC in terms of the sequence component, as you can see from this equation, in terms of BA0, and by taking the inverse of this matrix, we can also express BA0, BA plus, BA minus in terms of the BB, BA, BB and BC, and that comes out to be 1 by 3, 1, 1, 1, 1 AA square and 1 A square A. What is the difference between this matrix and this matrix? Number one, in this matrix there is a scaling factor of 1 by 3. When we take inverse of this matrix, we get 1 by 3. And also the second and third row have interchanged. That is, this is 1AA square, here it is 1A square A. This is here 1A square A, 1AA square. This matrix we can call it as the A0 plus minus matrix, because this transforms ABC into 0 plus minus sequence component, and this matrix can be called as AABC matrix because it transforms 0 positive negative sequence component to ABC components. So this is absolutely fine, there is no problem. If you go further, for example, you would have heard there is one more transformation called 1 by root 3. Sometimes in some books and papers they will use the term 1 by root 3 here. This is called unitary transformation, 1 by root 3. If this is 1 by root 3 and you take inverse of this, then you will again get 1 by root 3 here. So the magnitude looks like same, 1 by root 3, 1 by root 3. In that case, you will assume that the zero sequence, positive sequence, negative sequence component has only one zero sequence component, like let's say B0, then B plus and B minus. the energy is associated with these three components. Not like this, BA0, then BA plus, then BA minus. Then you have a BB0, BB plus, BB minus. Then you have a BC0 and BC plus and BC minus. Rather that, using this, we say there is a V0 which takes care of energy of all three components. There is a B plus which takes care of the energy content of BA plus, BB plus and BC plus. And then minus which takes care of energy content of BA minus, B minus, BC minus. I will discuss more about this when I discuss the load compensation using instantaneous symmetrical component. Okay, I will talk it later. But right now you understand that there are different kinds of transformations. Now, with this understanding, we can also express IA0 and IA plus IA minus is 1 by 3 of IA, IB, IC. Okay, this matrix is same because transformation matrix will not change to correlate the ABC to zero sequence, positive sequence and negative sequence component. And this is I0 plus minus in terms of the A0 plus minus. 1 by 3 will come here for that. Knowing this, we can make it more specific. Okay, what we can do, we can express in terms of the individual sequence component from this matrix. So from this matrix we can find out the individual components, that is BA0, BA plus, BA minus. As you can see that BA0 is nothing but 1, 1, 1. So this is BA plus BB plus BC by 3. And BA plus will be BA plus ABB plus A square BC, this row. And the third one will be BA minus equals BA A square BB and ABC by 3. So these three components are expressed as a function of BA, BB, BC. Similarly, we can write for current IA0, IA plus, IA minus in terms of IA, IB, IC. So this is IA plus IB plus IC by 3. This is IA plus AIB plus A square IC by 3. And this is IA plus A square IB plus AIC by 3. Okay, this is the individual expression of the sequence component. These expressions can also be used to define the unbalanced in three-phase system. If you remember, I had talked about unbalance factor. For example, you can find out the KU2 negative sequence unbalance factor as BA minus magnitude of this, okay, divided by BA plus. This is called as unbalance factor for negative sequence, or you can say KU minus. Similarly, we can define unbalance factor for 0 sequence component. It becomes BA0 here and divided by BA plus. So these are the terms which are normally used to define the unbalance in the three-phase system as a figure of merit, that how much system is the unbalance. Do you know how much unbalance you have in your three-phase system? Suppose if you are in the laboratory or if you are at home where three-phase is supplied, ideally the unbalance should be 0, but it is never 0 because nothing is ideal in this world. So when you generate the AC waveform from the generators, then you will get, because of the finite number of the teeth in the armature, in the stator, the output voltage is not perfectly sinusoidal, rather it is having some distortions. So because of that, this voltage is passed over transmission line, transformer, then transmission line, then distribution system. And when it comes to the distribution side, there could be 5 to 6% unbalance in the voltages. 5 to 6%. Current unbalance depends upon the nature of load. Okay, the current does not depend upon the source. The current depends upon the nature of load. Alright, so you have seen that the unbalance can be expressed in terms of this factor. Now let us try to understand, is there any significance of the sequence component in study of power system? Obviously it is, that's why we are studying it. The first thing is that these sequence components are very much useful to define and to understand, to analyze the nature of the power system, its behavior under different conditions. So the positive sequence component indicates the useful quantity in the power system. If system is perfectly balanced, then there are only positive sequence components. So as unbalance starts coming, the negative sequence and zero sequence component start reflecting. If you compute, you will find that there is a finite value of these negative sequence and zero sequence components. Zero sequence component has very special meaning in power system, particularly zero sequence current. Why it is so? We can understand from this network. Okay. Now, these are the possible configurations of three-phase system. This system is called three-phase four-wire configuration. There are three phases, 1, 2, 3, and there is a fourth wire, which is called neutral wire. The neutral wire is used to connect the load neutral to the system neutral. And on the way, it may be grounded somewhere. So finally, all neutral becomes grounded. This is called three-phase, three-wire system. Or configuration, where we have only three-phase wire, three-phase system, but there is no neutral which is connected to the source. Obviously, when three-phase system is balanced and has only fundamental, then presence of this wire does not make any sense except for protection issues. Because when there is some fault, then you have to sense the fault current through the neutral, the unbalanced current through neutral, then you require this fourth wire. And this current in this wire is called as zero sequence current. Why it is called zero sequence current, I will tell you. If you say IA, IB, IC, okay, if you sum these three currents, then you will get Kirchhoff current law. If you apply Kirchhoff current law at this neutral, we will get IA plus IB plus IC equal to this current IN. Or you can say, if all currents are in the same direction, then the summation of all three currents, all four currents will be equal to 0 plus IN will be equal to 0. If I change the direction of this current in this direction, then it will be equals to IN. This equals to IN. And what is IA, IB, IC? Is called zero sequence current by 3. Okay. So, of course, the I neutral, I divided by 3 divided by 3 this also, and this is called zero sequence. So 3 times of I A0. This is the relationship between the neutral current and zero sequence current. 3 times of zero sequence current of phase A will be the neutral current. And VNN will always be equal to 0 in this case, close to 0. That means IN may or may not be equal to 0 depending upon the balance or unbalance, but BNN is always equal to 0 because of fourth wire. If you see this configuration, then you see IN is always equal to 0 because there is no fourth wire. There is no fourth wire here. It's broken. So INN is always equal to 0. but B and N may or may not be equal to 0 depending upon the nature of load. However, B and N and BA0 cannot be as directly related as zero sequence component, this one. This is always true. But it's difficult to say that how BA0 is related to BNN. It is equal to BNN under some conditions. The condition is that for three-phase balanced load, if the load is balanced, perfectly balanced, that is ZA equal to ZB equal to ZC, if this is true, only in that case we can say that BA0 equals to BNN. Okay, I think I will discuss this in the coming classes. Actually, the expression for BNN in terms of the current is like this, that BNN is given as one YZA plus one YZB plus one YZC, this into BANYZA plus BBNYZB plus BCNYZC. Okay, so when ZA equal to ZB equal to ZC, then what will happen? We will have 1 by Z, 1 by Z, 1 by Z. So Z is common. Okay, and this is 1 by Z, 1 by Z, 1 by Z, 3 by Z. Here BNN equals to BAN plus BBN plus BCN by 3, and which is same as zero sequence component. This is BA0. So what do you see? This is not correct, so correct it. This is actually simply BA0. So only for this condition, when these three are same, and if you measure the voltage between this point, then it becomes BA0, zero sequence component. But if the impedances are not same, then we cannot correlate directly BA0 and BNN. While as the current expression for three-phase 4-wire system, IN is always equal to 3IA0. So zero sequence current is always measurable. Just put a ammeter in the neutral wire and you can find out the value of current, zero sequence current. Normally, for an ideal power system, the zero sequence current must be 0, the zero sequence voltage will be 0, and the negative sequence quantities must also be equal to 0. Now in the same line, we can prove that the energy is constant for both, that is ABC and BC transform. I describe this power as the geometric or vector apparent power. What is geometric apparent power? It is nothing but P plus JQ, which I have described in the previous class. In this particular case, the P is sum of PA plus P plus PC, and Q is sum of QA, QB, QC. So this becomes PA plus PB plus PC, and then QA plus QB plus QC. We can combine them on the phase basis. So this is A phase, this is B phase, this is C phase, which means we are adding the individual phase apparent power SA bar, SP bar, HC bar. We can also write in terms of BIA conjugate, BBIB conjugate, and BCIC conjugate. And this is again like a inner product of B and I, or BA BB BC transpose IA IB IC. It's like here the apparent power, the complex apparent power is the inner product of voltage phasors and current phasors conjugate. Now we substitute back in terms of the ABC parameters. This is ABC. So this is the A matrix. Transform ABC into zero sequence components. So ABC in terms of zero sequence becomes this quantity. Again, this quantity for current. This is conjugate, this is transpose. This is A and B transpose matrix. So transpose, in the transpose the order changes. So this becomes first here and this becomes second. This is conjugate of ABC. This is I0, I plus I minus. And if you solve this multiplication of these two matrices, you will find this is identity matrix 3 into I. And 3 into I is nothing but basically 3 this side here. If you multiply these two column vectors, you will get 3 into BA0 IA0 conjugate, BA plus IA plus conjugate, and BA minus IA conjugate, which is nothing but 3 into SA0 SA plus SA minus. So that means the energy, the power remains constant in both the transformations. Why 3 is coming? Because BA0 IA0 also represents B0 and IB0 conjugate, and also VC0 and IC0 conjugate. Similarly, this represents for B and for C, for B and C. So that B and C are accounted as a duplication of this term. Therefore, it becomes 3 times of the A phase component. Clear? So you have learnt in this class the sequence components, and also you have understood the zero sequence components. At the same time, we also have proved that in this transformation the power remains constant. Now in the next class I will talk about its applications and some examples. There is one more concept of this transformation, that is called instantaneous symmetrical transformation or instantaneous symmetrical component. That I will discuss when I talk about the load compensation using instantaneous symmetrical component theory.